So very quick review. Polar functions, or polar coordinates here, I should say, which is a more accurate start to this rather than functions, but polar coordinates are still being done on our xy plane. However, in xy or rectangular coordinates, we're told move a certain distance left or right, then move a certain distance up or down, which is why it's called rectangular. Whereas with polar coordinates, we're given a radius to move out from the origin from at a certain angle being measured from the positive x-axis, theta. So they're called polar because we're revolving around a pole, the origin, to get to the same point that rectangular tells us how to go left, right, up, down to get to. So polar, we're just being told go out a certain radius r at a set angle theta measured counterclockwise from the positive x-axis. In terms of how we do calculus with this, in pre-calculus, I would hope that you learned how to convert between the two forms. In our case, we rarely convert from rectangular to polar, but the way we deal with derivatives in polar is we do have to convert it into rectangular. The idea here is x is equal to whatever r is times cosine theta, y equals whatever r is times sine theta. So if I have the function r equals 4 times sine theta, and I want to change this into coordinates, well, I take r times cosine theta, so 4 sine theta times sine theta, that's x. R times sine theta, so I have 4 sine theta times sine theta, I get 4 times the sine of theta squared. And these are my rectangular coordinates. Well, then to find the derivative, since we are on the xy plane, the derivative, or the slope of the curve, is in terms of x and y, so I have it in dy dx, but my function is written in terms of theta. If you notice, it's actually written parametrically in terms of theta, that I have two variables, x and y, both written in terms of an independent variable, theta. So we find the derivative just like we do for parametrics. Derivative of y with respect to theta over derivative of x with respect to theta. So if we're taking our example here, if I take the derivative of y with respect to theta, it's chain rule with a power rule being done on the outside. I get booth 2 down 8 times sine of theta the first, but then derivative of sine is cosine. That's going to be the numerator of my derivative. Dx d theta, I have to do product rule on, but this will then give me the denominator. Now, if I wanted for some reason to get the second derivative, it's done just like with parametrics, where I take the derivative of this with respect to theta divided by dx d theta. But this expression gives me the slope for my curve at any angle theta. So if I wanted to find the tangent line when theta is pi over 2, I just need, first of all, a point, which, because I have my parametric form, I can find the x and y's by just plugging pi over 2 in for that theta. I get x is 0 and y is 4, so I'm going through 0, 4. And then I need the slope, which I just need to plug pi over 2 into my dy dx. And I get slope is 0. So I have enough that I can write the equation of my tangent and get y equals 4.